Hello, everyone. Good afternoon. Welcome to, it's day two, right? Yes. It's been a long week. So yes, thank you for coming. My name is Jimmy Bogard. You can find me on Twitter at @jbogard. This presentation will be on my GitHub. I promise I'll push it soon, I'm sure. github.com/jbogard. And I blog about this topic and a lot of other things on my blog at jimmybogard.com. For my day job, I'm actually the chief architect of a consulting company out of the States called Headspring. And so a lot of this talk is really about some of the experiences I've had dealing with microservice communication patterns. So a lot of the clients that I deal with have some kind of really large existing legacy system. These systems have been around for sometimes even decades, and they've run the core of the business for years and years and years. But at some point, those systems that are running the core of the business can no longer meet the needs of the business. They can't change them easily, they can't deploy them easily, and they find that just progress more or less grinds to a halt. And so they start to look at alternatives, say how can we move faster, how can we better meet the needs of the business. And those existing systems usually have some kind of bad name, like monolith, for example, and they want to move from that monolithic system to something smaller. Now, there are some good things about those big systems. Like you can just call any code you want to from anywhere in the system and it all works okay. You don't have to really worry about how different components need to communicate with each other. And when those organizations move from these very large single process systems into lots of smaller systems, it introduces the problem or the challenge of these components and services needing to talk to each other. Now, before we get too far, I did want to clarify one thing about, I put microservice in the title because that kind of guarantees it gets accepted. Let's first talk about what do we mean by a microservice? Because that kind of helps set up later on when we talk about how we think about these kinds of systems. So the original definition for me didn't work well with any of my clients because they would say, yeah, we're doing microservices. I look one level below. I'm like, no, this is just like a bunch of REST APIs talking to each other. It's not necessarily what microservices are all about. So I had to think of a definition that would be more appropriate for my customers. And this is what I came up with. A microservice is still a service-oriented architecture. So all those things in the early 2000s that everyone went away from, there were some good bits out of there. So it's a service-oriented architecture in which we try to focus the design towards the smallest, still autonomous boundary. And that autonomy is kind of the key thing for me in a service-oriented architecture. And autonomy basically means that this service can take care of its own business without having to worry about other things blowing up and affecting it. So when I'm looking at moving from one single system to lots of smaller systems, and suddenly I have this problem where if this one system way over there goes down, that affects my ability to do anything, then I have to figure out how do I handle being able to coordinate these kinds of activities where I can still stay up and stay alive and be able to do the job that I was supposed to do and not worry about that other thing going down. But that's a very different kind of way of building systems from those single monolithic applications. Like if something blows up in a monolith, right, just like get an exception, you get a stack trace that tells you exactly where the failure was. If you see a failure in a distributed system, now that stack trace is actually distributed amongst many log files amongst all your different services. So if I'm trying to build a system that's resilient and can stay up and handle those kind of failures, I have to have a different way of thinking and a different way of organizing my systems. So when I'm looking at taking those big applications and breaking them down into smaller pieces, you have to then ask, well, what are those small pieces going to be? How do I decide what's going to be over here versus what's going to be over there? And then finally, how are these things going to communicate with each other? And what I find is there actually is a lot of parallels between real-world systems, that is like human people-based systems, and the kinds of systems that microservices are good for. And if I can look at a real-world system that is using humans as an analog for microservices, and I see if those kinds of communications and kind of patterns would work in the real world, then it has a very, very high likelihood of success in the virtual world. So in a lot of the organizations I work with, all of our design exercises are really substituting these microservices for people. And I'd like to see, well, if people were trying to do these different jobs, how should they communicate to get things done? So a lot of the problems that we see in the real world of scaling up something small and trying to go big are the exact same kind of problems that we will see in our virtual systems, our microservice-based systems. So if I'm looking at a system and I want to scale it up, it's gotten too complicated, too big, the same kinds of solutions I would see there are the same kind of solutions I would see with microservice-based communication. So a good example of this is looking at human-based systems that have existed for decades or centuries or even millennia. And these kinds of systems still have the same kind of scaling problems that we see in the virtual online world as well. So things like restaurants and mail order catalogs and those kind of things that are very people-based have a very similar kind of issue we see with any kind of online system as well. So I looked at existing human systems and tried to find, okay, what are systems that I see in the real world that start very small and then I need to scale up? Now, I live in Austin, Texas. For those of you that don't know, that's a very hipster city. It's like the sea of sanity and a very big ocean of like guns and stuff, being in Texas. And so being a hipster city, we have a lot of these hipster food trucks. Again, something else we've gentrified and made hipster are food trucks. And so in our office complex, we actually have a daily food truck that comes. And they always have these like kind of clever names. The one I really like the best is this hot dog cart. They like hot dogs, that can't be that interesting, except they deep fry the hot dogs and then wrap them in bacon. So they're just absolutely like actual proper, like streaky bacon, not whatever you have here, like good bacon. And so, it's absolutely delicious. But this food truck is just run by one single person. So I want to look at that business model and say, okay, if I had this very simple process, how would I take that business and start to scale it up? So in this business, it's just one person doing every single step of the process. So when you want to get that awesome deep-fried bacon-wrapped hot dog, you go up and you go to the front counter. You place the order. You don't leave that spot until you finally receive that delicious deep-fried hot dog. So in this kind of business, everything is done by one single person. Everything is synchronous. So I'm just standing there blocking everything until I'm done, and everything is essentially in process. So that kind of system sounds very, very familiar to me because it's a single in-process system where the application does absolutely everything. So this is almost exactly like our traditional in-tier monolithic architectures where everything's inside a single process. Sure, like it's kind of simple because everything is just in that one system and one application, but it becomes very difficult to scale this kind of system out. So those food trucks in the States are pretty expensive to run. Like it costs tens of thousands of dollars for licenses and all the regulations and things like that. And you have to like find a good spot to park in to be able to make sure that you're able to make up whatever losses that you have for the day. And so they'll go around and find like high traffic areas to make sure that they can kind of maximize the amount of revenue they'd see in a single day. So if I'm coming to start one of these businesses, I have to figure out like, well, how much should I actually charge for the items I'm going to be selling to people? And I can kind of walk backwards and say, well, based on how much my food costs and kind of working backwards from there, I can figure out like what my per item cost is to me, and then I have to figure out how much to charge on top of that in order to make sense for me to be at any given place. So when I'm backing that out, I get money by people ordering stuff. And so if I want to figure out what's the most amount of money I can make, I basically just look at how long does it take to process an order and then back out how many orders would I actually see in a given amount of time. So I can break it down into individual steps of everything that happens within one single transaction in this business. So you have the initial taking of the order. And for this, it takes like 30 seconds, which still seems like a long time, but this food truck place has like especially clever names, like the hot dog, the grilled, the deep fried hot dog with bacon and kimchi on it. It's called the Kim Dog Il. Oh, I know. And so you're going up there, you have to like translate what this clever name means into an actual food item. So that's why it takes like 30 seconds for you to actually order. And from there, there's a certain amount of time for each individual step in the process. And finally, you get to the end, you say, well, if it takes 2.5 minutes to be able to complete a single order, that means I can just divide that by the number of minutes in an hour and say the maximum number of orders an hour I can have is that number of orders I can have over time. However, if I actually look at the real statistics behind any one of these food trucks, it never comes close to that maximum ever. And why is that? Well, there's a few complications here. First of all, people don't like to wait in queues. Like, well, in the States we don't, okay? I know that's a thing here, but we don't actually like to wait in queues. And so if I see a long line of people and I'm walking up, then I see that long line and say, well, I don't want to wait that long. I'm just going to go find something else to eat. The other thing we find is we never see a constant rate of flow. So even though it takes 2.5 minutes per order, we don't see one person arriving every 2.5 minutes. And instead, we're on our Slack, we're saying, okay, it's time to go get our hot dogs, who wants to come with me? And like a group of 10 of us go down to go get our food. So we'll see these really big peaks and valleys in the number of people that are waiting in line. And I know, if I say it's like 2.5 minutes per order and I see 10 people in front of me, I can quickly do the math to say I'm not going to be out of here in the next 15 minutes or so. So because there are people involved and the people don't like to wait in these queues, then we see a much lower throughput than that theoretical maximum of 24 an hour. Because again, someone coming in seeing a very long line, like, oh, well, I'm just going to go find something else to eat. Now you could say, why don't us as humans just alter our behavior when we're going out to get lunch? But no one gets lunch at 12:04, right? They have like these specific times they want to go, so we can't just say, well, we'll just kind of go upstream and say people just need to come in at a more regular pace and like just relax here. No, we are going to go down as a group so we can still like talk and whatever. And so at this point, this guy's business model starts to fall down because they see that I could easily make a profit at 24 an hour or 20 an hour, but what I actually see is much less than that. So what I want to do is maximize the revenue I can make in the time I'm going to be there. So how can we fix this? Well, the first thing we could do is scale up, right? Well, what does it mean to scale up in this system? Like buy a bigger food truck? No, that's not really a thing people do. How about you just like duplicate the food truck altogether? So I had one food truck, now I have a second one with exactly the same setup. But there's a huge overhead in being able to get that food truck license and whatnot. So you don't see like food trucks just get duplicated all over the place. They've got basically the one. But the solution, of course, is going to be what everyone does, just hire more workers. And each individual worker is going to specialize in one aspect of the overall process here. So when I have each person doing one individual job, they can optimize how they perform that individual step in the overall process. So originally, when I walked up to the counter and ordered something, I would not leave until I'd received my hot dog. But in this case, we can start to optimize the process and say, maybe we can actually do several things in parallel. Maybe I don't just do one order at a time. Can I do multiple orders at a time? And if you see these kinds of systems, what we tend to find then is that the only queue, the visible queue that we can see going on is the ordering process itself. So if I'm able to do this, and now ordering is the only bottleneck, my actual maximum amount of orders I can take an hour is not that 2.5 minutes anymore. It's now that just down to that 30 seconds per individual someone trying to take the order. So my theoretical throughput now can go through the roof. Instead of 24 per hour, it's now way up to 120. Which, by the way, looks great for like, if you needed to get a loan or something, like, look at how many orders I can take. But there's a problem now. How do we actually fulfill an order in this sort of process? I now have to have these individuals somehow communicate with each other, and us as people have to figure out what does that communication need to look like. How do I ensure I'm still able to complete orders, and how do I make sure that the customer is actually happy at the end of the process? So some problems we have are, one, the transactions are no longer synchronous. So originally, I went up to the window, I made my purchase, but I, as the customer, did not leave that location until I received my food. In this model, though, we only stay at the counter until we've paid. And after that payment is successful, we just go off and mill about over to the side over there. But us and humans in the real world, like, does anyone complain about that? Like, no, I want my food now. We accept that as a trade-off to say, yes, I'm not getting my food immediately, but at least it's getting ordered and processed quickly. Well, I have to have these different people in the process somehow coordinate with this activity of being able to fulfill this order. So how do later steps know what to do based on the things that have happened before? How do we know when we're done with an order? And the solution to all of this is going to be some kind of communication and some kind of messaging. So what I do with my customers is basically draw these kinds of whiteboard diagrams where we have like a box indicating that this is a microservice, kind of cross that out, and I literally will draw a human being to say, pretend this is a person. How would these two services, these two people, try to collaborate on some kind of interaction to be able to get this overall business transaction complete? And what we'll do is I'll look at every single interaction in the process to figure out what makes the most sense from an overall business perspective and from a user perspective for each individual interaction. So the first interaction is going to be placing that first order. Now, one of the things I see a lot of people making the mistake of and moving from a monolithic architecture to a microservices-based one is they just want to have some kind of blanket strategy for how everything should communicate. It's like everything needs to be REST, or everything needs to be gRPC, or everything must be events, everything must be some kind of messaging. What I find is that no one individual communication pattern or solution is going to magically work in every single scenario. And we do have to actually design and think about every single situation to understand what makes the most sense for any given step of the process. So in this first step of the process, what would be the most logical interaction for a human coming up and being able to place that order? Well, first we have to figure out like what information we need to capture from this. So from the customer, I need to know what food you want. And I need to know how to notify that customer that their order is ready because they're milling about over to the side. So from that initial interaction, what is the most logical sense for that kind of communication? Well, it's probably going to be some kind of synchronous communication. You probably wouldn't use like async messaging. I don't go to a lot of restaurants where you don't directly talk to the waitstaff. You like write down a piece of paper and slide it over and then look at it on the other side. Like that's not usually a thing that kind of happens. So for this one, we want to have that very fast interaction to be able to make sure we complete this order. And so for this one, we'll pick some kind of synchronous communication. We also notice that it's just the person talking back and forth. The customer coming to the window does not actually write anything down. They just tell the person what they want, and the other person on the other side, they write it down, but it's not the customer that's actually writing anything down. So for this initial order process, I would choose something that represents a synchronous, non-durable form of communication. And so if I try to translate, well, what is the analog to a verbal communication in the real world into our online world? And for that one, it would be probably some kind of REST or RPC communication. So if I look at something like HTTP is synchronous, it's request response, right? I make a request to a server, and the client is sitting there waiting for a response to come back and say, yes, I've received your acknowledgement. It's also not durable. So if something goes wrong with the communication, no one's written it down, you may have to retry that interaction again. And we see this in the real world as well. So if I'm talking to someone and they're not paying attention, like you snap your fingers like, hey, I'm talking to you, and then you have to repeat yourself. And similar thing in this kind of interaction initially as well. So if we're making that first interaction as a synchronous call, we have to be able to handle to make sure that, if something gets lost to communication or that can't communicate for whatever reason, then we'll have to be able to retry this. So our first initial interaction is going to be just a HTTP web service call. So what patterns can we see here initially? First of all, it's going to be a synchronous request response. I'm going to synchronously call your service to say, I want to place an order, and I'm going to sit there and wait until I get some kind of response. So that's the easy one, right? Like, okay, yes, I have that initial interaction, synchronous, everything's good. Now, how do I deal with all these back-end folks? Like the people that don't have to actually dress nicely to go to work, they're in the back, they're messy. How do I deal with all of those folks? Do I have durable or non-durable communication between each of these different folks? Who is actually going to manage the overall process of that order moving through the system? And if something goes wrong, how do we manage those failures? So for each interaction, I'll look to see, based on my different patterns available, let's just try one and see, does it make sense? So let's look at the first one. That is, I have to communicate from the person taking the order to the people behind the scenes, here's the order information. So we could do just a synchronous request response. And you'd see this in the real world as well. So in that kind of situation, you basically get the order person taking the order, and then they're yelling in the back. got an order for this. And you see that, right, sometimes? I've been to restaurants where I hear like constant yelling going on behind the scenes of people barking different orders from each other. And so it could look something like this, where I just say, yes, I need you to process this order. And then hopefully they're listening and return back, I got it. But sometimes they're not listening. Sometimes they're busy actually making orders. And so it could be the case where I say, hey, I got a new order coming up, and I don't hear any kind of acknowledgement. So I'm like, did you hear me? We got an order coming up. And so I may have to retry that again. And what's really going on is like they're busy. They're performing the work of the previous order. And so if you're trying to talk to them synchronously, they have to stop what they're doing, turn around like, I got it. Okay, here's the order. Okay, and then go back to actually doing their work. So what happens if that other side is down? Like 503, service unavailable. In the virtual world, we may just like try to scale that out and be like, well, just put that in Kubernetes or something and have some kind of auto scale, whatever, that just keeps scaling out forever. That still doesn't handle the situation of something getting timed out or something not going through successfully. So I could say, yes, I'm busy, I can't do anything, so let's try this again. Okay, you're not paying attention, I'm going to tell you to make the order again. And it's like, okay, I got it, geez, I can finally do this. However, how do we make sure that they didn't actually hear the first time, they just never returned a response in the first place? So they actually did successfully retrieve the first order information. They just didn't tell me that they got it, and I was tired of waiting, so I just moved on with my life. And if I then tell them there's another order, how do we make sure that they didn't actually make two of the same thing? So if I try to make that post again and say, I need you to actually place this order, and this lady tell me, I got it, but then out the other side comes two orders. And so I want to make sure that if I have this non-durable form of communication, and I'm now introducing the possibility that I'm retrying my communication over and over again, then we need to make sure that, or at least handle the fact that the receiving side may receive that communication more than one time. So there's a word for this, idempotency, and this is just a fancy word for saying if you ask me to do the thing twice, I only do it once. And we have to figure out like what makes sense in order to be able to handle receiving messages multiple times but only actually doing the work once. So from the actual other side, I need to have some way of knowing, was this the same order as something else or not? It also looks something like, it could be something like a fire and forget sort of message, which is I just tell you the order, I just tell you I need you to process the order, but I'm not going to wait for a response. It's not going to do it immediately. It's going to be doing it sometime in the future. So in this case, it receives the request, and it's like, well, I can't do this right now, but I've received it, and I'm going to do it sometime in the future. So it says, yep, I got it, thanks, but I'm not going to do it right away. I'm going to do it sometime in the future. At this point, we need to worry about how to flow my orders across these different places. And you can still see this in real life. A picture I have up here is a burger joint in Austin, Texas, called Mighty Fine, and the burgers are mighty fine. And their actual paper bag in which they take the order on contains, like, here's the instructions for what to do. And that order written on the bag will actually flow through the entire system. And on that bag are the instructions of exactly what to do along each step of the way. So this kind of pattern where I up front am able to determine here are all the steps necessary to be able to process this order is known as the routing slip pattern. And in this case, the initial person at the very front of the process looks at the order and writes down the steps that need to happen as part of that initial message. So in this case, I can look at the order and say, right, these are the steps. It needs to go to the dress step, the grill step, the pack step, and then I finally give that order to the customer. In a messaging world, that set of instructions will be included on the message, so each individual process along the way receives the message, sees that step, performs that step, and then forwards that message to the next step in the process. So there's not like some central person that's managing the flow as the pieces go through the steps. It's just a simple straight line through the process, going one step at a time until it gets to the end. Now, there could be some times where I have extra steps or fewer steps. So in the burger joint, if I ordered like a milkshake, well, that would be one extra step in the process that order needs to go through, but that could all be easily determined all the way up front. So each of these different steps of the process will have some kind of queue to manage their own individual set of work. And in real life, we can actually see this. If you have a paper-based restaurant, you'll actually see order tills, where they get a slip of paper that is the order instructions, and they put it physically on this board with clips. And as orders are completed, they move the orders down in the till. So they've been able to define a queue for the overall process. By having each of these messages asynchronous, we remove the problem of making sure that everyone is listening at all times to make sure that communication drops. I have to retry the message. If I go through queues instead, I don't actually have to talk to the dressed person directly. I can just put the order on the table, and then at some point in the future, they'll take that order and put it up on their board. And then finally, I have independence maintained for each of the steps, because each step then can decide completely internally how they're going to process each individual step in the overall order and optimize it accordingly. So the grill person can be like, well, you know what? I can actually cook 10 hot dogs at once. I don't have to do one at a time. So if I see a big group of people coming and walking up, let's go ahead and drop 10 hot dogs down. And by the time we got through the order process, then all of those hot dogs will be ready. So this is kind of a very straightforward sort of process. And we have used this sort of pattern in our systems, where I have a very linear, very deterministic process. But I do find that as I start to add more and more services, this kind of simplified flow starts to fall down. And so I have to start looking for more interesting and more exotic patterns to be able to handle more complex flows. Now, a lot of these patterns that I'm going to be talking about were actually all written down in a book called Enterprise Integration Patterns. Now, that book is kind of a lousy name. It's really just messaging patterns, because it really it sets the stage as, here's how you get services to integrate with each other. Here are 3 ways that don't work very well, but here's a way that works really well, which is messaging. And so a lot of the patterns we see, I'll be talking about, are actually just completely defined already as part of that system. Now, there was one part, though, in the book where he says, okay, if you go past just simple request response, simple routing slip, there's another pattern for you called the process manager pattern. And this pattern lets you do really complex stuff. And then in the actual text is someone should write a book about all these patterns that exist for process managers. Well, that book was published 15 years ago, and there's never been part 2 yet. So unfortunately, we have to kind of fill in the gaps of what we see as those more complex conversation interaction patterns. But I can still take this very simple system and try to scale it up in different sorts of ways and look at what kind of patterns emerge from those systems to be able to apply it into the virtual systems that I deal with. So we're going to kick this up to 11. And look at how do larger systems deal with this more complicated sort of scenarios. And if I look in the real world to say, well, what larger systems take my food truck concept and go global, that's what fast food is, right? It's industrial food production at a massive distributed scale. So if I look at something like McDonald's, which by the way, I actually worked at a fast food joint growing up, so I can actually speak with experience to how these systems are built. They're much more complex than our very simple food truck scenario. The food truck had one item with different toppings, and that was it. So you can have a very simple set of processes for that simple scenario. But in this case, it's much more complex, and they're really trying to optimize throughput here. So in this case, a lot of the steps are actually independent from each other. You don't have to have a specific order in which some things happen. But sometimes there are some dependencies between individual steps. So in these fast food joints, they have a specific grill station, and they have a separate station they call the dress station, which is basically putting the toppings on your sandwich. Well, you have to finish grilling before you put the toppings on the burger, and so there is some natural set of dependencies between those 2 parts of the system. Based on the order, I'm going to be doing different set of activities. So someone may just come in and order fries, and someone else may come in and order just burgers. And my overall process needs to be able to handle those different kinds of orders coming in with the different kinds of processes. So how do we manage this then? Our very simple process of just making the bag go from one step to the next, won't make a lot of sense because, again, what if someone just orders one item or the other? I'm going to have a lot of orders coming through one step in the process that don't make sense to. That's going to cause some inefficiencies in this system. So, again, let's look at each of these interactions in turn and figure out what makes the most sense from both the customer perspective as well as the overall business perspective to figure out what is the right interaction model for each step of the process. So the first one, taking an order. This has changed over the years because McDonald's does now have like the kiosks, but I don't trust those because like the person in front of me may have had like the coronavirus or whatever. It's like I don't want to touch that screen that everyone else has touched. I just want to tell you my order. So let's just pretend we don't have those like giant touch screens with lots of germs, and we're still just verbally telling them the order. So in this case, it'll be very, very similar as our food truck. The initial order is still going to be as low overhead as possible, so a verbal communication or a non-durable form of communication. And as part of that interaction, I'm not actually creating your order at that point in time. I'm just receiving your order, and then in some kind of back-end process is actually going to take it from there. So in this picture, that initial order is going to look very much the same. I'm going to make some kind of synchronous request, whether it's a web API or it's an RPC call. The overall idea is that it's going to be some kind of synchronous communication in which after that response is returned, it's not actually fulfilling the order at that point in time. It's just acknowledging, yes, I've received your order, and go please sit down. Okay, so I received the order. Now how do we actually process it? I could try that simple routing slip, just have the order go through all the different steps, but that's not very efficient. I have lots more steps going on, and so it's going to take a long time for that single message to make it through all the different steps if I'm going to have to do one single step at a time. So synchronous is also completely untenable here. Like, I'm not going to stand there and be like, okay, burger person, I need to drop the burger. You got the, yeah, I'm going to drop the burger down. Okay, fry person, I need to drop some fries down. How many fries? 3 fries. Oh my God, it's like everyone's starting to freak out. So trying to do this as some kind of synchronous operation would be completely untenable in the real world and doesn't work really well in our virtual world either. Routing slip is too inefficient, or routing slip, excuse me. Too inefficient. I'd be going to too many different steps, and if something goes wrong, I can't easily recover from those failures. And so the solution is going to be some kind of conversation pattern. There's some agreed upon upfront way of managing all these different pieces through a more complex communication, which we would call a conversation. So how does the real world do this? Well, first of all, they're not using any kind of synchronous communication to each one of the steps. That's just not going to work very well. Instead, what they're going to do is some kind of broadcast or publish of this event that has happened that says, hey, an order's been created. What information do I see in the order? It's just going to be that just a link or a URL to say, and here's all the set of order details that you can go find. So in this case, the person at the register doesn't really know or care about all the different subscribers to this set of information. Instead, they're just letting the rest of the restaurant know, hey, I've got an order that's been created, and that message then gets sent distinctly to each one of the individual subscribers. Now, the real-world systems are more complex. They can look at the order and say, right, this order doesn't have any fries in it, so we're not going to send that order information over to the fry because they'll just disregard it and ignore it. Some of them aren't that sophisticated, and we'll just broadcast out the order to all the interested parties, and then each interested party then has its own queue to be able to handle their specific set of order details. Now what about completion? How do I figure out when an order is done in this kind of picture? Well, how does McDonald's do it? The way McDonald's does is when you go up and place your order, what do they do with that? They then immediately take a tray and they physically put a tray down on the table to keep track of the items in the order. So that's what the cashier does. They go out and they put the tray down, and that physical tray will hold all the items as the order gets completed. Then there's a receipt they lay down on the tray, and that receipt shows all the items in the individual order. But I still need to figure out how to coordinate this overall activity. So let's just walk through the process. So this first step completes. So that person takes the completed items and then they place them on the tray. Once they place that item in the tray, they look at the receipt and check the receipt based on the items that they see on the tray. And if all the items are on that tray, then the order is done. But in this case, nope, not done because not all the items are on the tray. Second step in the process goes. Person completes, they put the items on the tray. They check the items on the receipt for the doneness of the overall order. They say, nope, everything's not completed yet, so I'll go back to my station.
I'm listening.
Oh, no, Siri. So finally, I get to the step that does finally complete the order. So this person takes the items, puts them on the tray, checks everything on that receipt for doneness. Finally, everything is done, and now I need to notify the customer their order is ready. So this pattern is known as choreography. And I wish these had different names because I never get the difference between these two major patterns because like no one's dancing here, but I guess that's what we're calling it. So in choreography, we have more of an event-based initiation. So something kicks off the overall process, and typically in choreography, it's an event that gets sent out to multiple parties. The step order is not necessarily enforced here, so I don't know exactly what step in the process is going to complete before others. Like sometimes for a given order, the fries may complete first. Other times, the burger may complete first. I don't know, but there's no real dependency between those two steps, so I don't really care which one finishes first. I just need to have some way to track completion. So in a choreography-based conversation, something needs to keep track of like where I am in the overall set of our dance here, of people coming in and finishing things. So a lot of times, I have to have something that tracks that completion. So that's why that receipt is on the tray. The receipt tracks the overall completion of this choreography. I called this years ago the observer pattern because you're observing events, but the microservices world called this choreography, so I have to use their word instead. Okay, that's not enough though, right? I finished the order, it's done, but now how to actually deliver it to the customer that is sitting there waiting for it at their table. So I need some way to correlate orders with people. And this is known as the correlation identifier pattern, that I'm coordinating some activity with a final completion step, and there are a few ways we can do this. Now, how does McDonald's do this? I admit some of you still go there, right? Or there's Five Guys, whatever. It depends, right? So I have seen some places that use some kind of natural correlation identifier. So like a Starbucks or coffee shop, they like to be personal to you, like make you feel good about life because it's hipster and all that stuff. So they use a natural correlation identifier, which would be your name. But that's not always great. Like if you have a common name, like Jimmy, well, I guess James is more common, then they'll have to distinguish between like Jimmy with a cappuccino versus Jimmy with like the iced mocha frappuccino, half soy, half whatever. And so they'll have to like also name it. So the name can work, but there could be the potential for collisions. So we have to make sure that it can still uniquely identify this process based on that natural correlation identifier. Well, if that's not going to work for us, then we can choose an artificial correlation identifier and just make something up. Like restaurants, for example, use an order number. So it's just some increasing number that goes from like 1 to 99. And when they get to 99, it just starts over at 1 again because they don't have 100 orders ever going on at the same time. So it really doesn't matter. We just need to pick one for our individual process. And so depending on what we're doing, we either have to make something up or we can kind of grab what we see already going on to say, this makes sense for overall correlation identifier. Like an e-commerce situation, they would just generate an order identifier based on your cart information. Say, this is your order ID. And then some like gobbledygook thing that you can get in your email, whatever. They're not going to be like, hey, this is Jimmy's order. And as it goes through the process, like Jimmy's order is ready. These big systems don't do that. So this kind of process works really well, except for the fact that it does introduce the possibility of failures in our system. In this picture in particular, it puts a lot of onus on that employee to be able to correctly check to see if my order is complete. And they always get that right, right? You never have anything missing from your order. So what do you do as someone receiving this order? Like the first thing you do is you open the bag and you check the contents because something's always missing. And that's because this is a naturally messier solution because no one's really controlling the entire process. But it is a lot more scalable because I'm allowing a lot more steps to complete in parallel, independent with each other. So this is more like a cookie cutter complex system. What about other restaurants that are bigger and more complex? So in a real restaurant, like a sit-down actual restaurant, the orders can be much more complex. People can order all sorts of different things and make modifications to things. And one of the things that's going to be quite a bit different is the prep time is going to vary wildly in these kinds of scenarios. So in this case, timing matters a lot more. I need to make sure that when I deliver the food to the end customer, that they don't have like, their steak is cold or the mashed potatoes are hot. I need to make sure that everything is completed more or less at the same time. So in this case, I need to have a lot more control over this overall process. In a fast food sort of place, like they're just churning out fries all the time, so it's not necessarily made to order. But in good restaurants, right, your food is actually made to order, unless you go, I guess some chains is still microwave junk, but let's assume you're going to a good restaurant. So who do they have here to help control this process? This guy. Where's the sauce? There were much more worse memes for Gordon Ramsay, but I don't have too many curse words here. Okay, so yeah, you have some kind of like benevolent dictator who is the chef, and they're the one that's actually controlling this overall process, making sure that your food gets done on time and it will be delivered out the door. So in this case, the chef will receive incoming orders from the waitstaff. And then based on the things they see on that order, they will create a plan for completing that order within a certain amount of time to make sure that everything is more or less done at the same time and it can go out the door. And in order to do so, they're going to be barking orders at people at specific points in time to say, I need this, I need that, do this thing, do that other thing. So it all starts off with a waitstaff though. And again, this is something you have to actually design, like all the way from the very initial customer interaction, you have to figure out how those steps should be done. So in this case, what we're doing is adding items to an order. That is still a synchronous communication between the customer and the waitstaff. So yes, I want to add a burger to my order. I want to add some fries, and of course, a pint of ale or lager, whatever suits your fancy. Okay. So once the waitstaff has received all this information, they wait for this, they say, is that all? Anything else? Say, no, we're good, so go ahead and finish the order, and now this poor waitstaff has to go to like the devil in the back, which is the head chef. So they'll let the chef know, yep, my order is done, and now you can go ahead and do stuff. So at this point, the chef is then going to build out that plan in their head of exactly how they're going to coordinate all these activities based on the expected completion time and cook time of everything going on. They also have to balance like, okay, this specific station may be backed up, so I may have to wait a little bit longer, but they're the ones that are really kind of controlling that entire process. By the way, I've never actually worked in a restaurant. I just like watch a lot of it on TV, and this seems to be how things actually go behind the scenes. I watched Ratatouille a few times. I think that's kind of I don't know. So this head chef is no longer using events because he doesn't trust the individual sous chefs or whatever they're, the other people behind the scenes to be able to make those decisions about what should be made when. So they're actually going to be using more of a request-response pattern to say, hey, I need you to make this thing. Hey, I need you to do this thing. Oh, I received a response that the thing is complete. Now I'm going to send that command to go ahead and deliver that item to the customer because we want our beer first, right? Yes. Now I receive a message that says I want to send a message out to the fryer saying, okay, now burgers take a little bit longer to cook or steak or whatever. So I'm going to wait a little bit. And then when I feel it's ready, then I'll send that message out to the other person to say, go ahead and start this next step in the process. Now, as things complete, they're replying back to the originator saying, I've now completed this item, and I've now completed this item. And the chef, keeping track of everything themselves, once all the items are complete for that order, finally they can, again, bark out the order to the waitstaff to say, ready, right, now it's time to actually deliver this order to the end customer. So this pattern, in which I have this benevolent dictator in the middle, who is directing all the work that needs to happen using request response or commands and replies, this is known as orchestration. Again, I think the people coming up with these names like music and dancing, so we have choreography and orchestration. So the idea is that you have some conductor that's telling the entire orchestra what to do. In this case, I have that head chef that is directing all the different items that need to happen. So in this case, instead of this process starting by a set of events coming in, instead this process is started out by some individual message. And then from there on out, we're using request response or commands and replies to coordinate all the other services, telling them exactly what to do. The responses coming back typically indicate the completion or the result of that operation, or it comes back and says, the sauce is burned, I need you to retry the sauce, or let's just put it out the door anyway. But it's really the person in the middle that's making all of the decisions about exactly what to do based on these replies of these different steps completing. So in this case, there's a lot less tracking of individual status because the person in the middle is the one that's really doing all the coordinating of all the different work. So they'll know in their head, well, I won't start this step until that other step completes. So they don't have to keep track of what is done when, because they've basically got the workflow in their head of how things need to operate based on the individual replies coming back. So these are kind of two competing sort of patterns where I have one that's more command-based in orchestration and one that is more event-based in choreography. And again, this is one of those things that people new to microservices want to put some line in the sand saying, we are only doing choreography because events are good, right? So let's do choreography. And other folks no, we want complete control over the system, so always do orchestration. But again, in the real world, we see that those kinds of patterns make sense in some scenarios, but don't make sense in others. So we still have to analyze the overall business goals and interactions we want to have to determine which one of these things that will make more sense for our overall situation. So we do this by looking at the process flow and looking at the coupling between individual steps. Does this step depend on that step, or can it be done completely independent of each other? So what we usually see come out of this then is choreography is something we usually do inside a service boundary. Wait a minute. Oh, I think I have these backwards. This is why I hate these names, orchestration and choreography. It's usually actually orchestration inside of a service boundary. Just cross that out. Orchestration usually inside of a service boundary, and choreography usually between service boundaries. And the reason why we have this is because if I have a set of services who only communicate with commands, then it's going to feel like that, the jerk chef who's barking at everybody, all these different orders, and there's no autonomy. I can't just do what I need to do outside of you yelling at me. And so you see a lot of those interactions be very command-oriented or RPC-oriented. So that introduces process coupling and sometimes even temporal coupling in which that person is yelling at you and you have to be paying attention, otherwise they'll get even more mad at you. So if I want to avoid process coupling and temporal coupling, that's why you would usually see choreography as something you have between services. Now, if I'm inside my service boundary, then I can do whatever I want because it's my business how I get my stuff done. So inside of my own service boundary, that's why you see typically more command-oriented sort of conversation patterns. So I wanted to finish up looking at the read part of this whole enterprise. That is, up until this point, we've really been talking about how to fulfill an overall business process. There's an important piece here in that in our systems that we build, in the real, our actual computer systems, we have to worry about these systems being able to handle the read side of things separate from the kind of business transaction backend part. So if I look at the real world, what is a similar kind of scenario that they would see? This is very similar to menus. The menu you see when you walk into a store is that very cheap read side of the system. And reading that menu is very cheap, right? It only costs whatever the light energy cost is to take that light and bounce it off the menu into your eyes. That's the cost it would be to read that menu. The other thing we see is that menu is built directly for the customers involved. Everything on there is designed for you to buy stuff and pay the money and get an order. It's completely kind of cut off from however the backend was actually used to build that out. It's 100%, we're designing this exactly for what the customer needs. And one thing we're not doing is we don't want to expose the decisions and business logic of how that menu is created to the end user, where ideally we're just building that menu and that read version of our world to be able to accomplish that business goal of like getting the customer to buy stuff. Now in the real world, how would the business owner create the menu? Well, it's not easy. Like you have to figure out where you're going to get this different food. If you have some exotic menu item, then you have to figure out, well, how is that going to impact the overall bottom line? How do I charge for it? Do I charge the same thing for every single place in the world or even one given region? So those back-end systems are optimized for managing the menu. They have all the decisions and business rules about how to add new items and change prices and things like that. And it may even do more complex analytics, like looking at the future saying, well, I know pork prices are going up or down, which is why you see the McRib sometimes, by the way, in the States. Like pork futures go down, and so they buy a bunch of pork, and then McRib is back. But that's all built in these back-end systems that they're not exposed to the end user. All you see as the end user is a billboard that says McRib is back, and you go eat that nasty pork. So yeah, all these kinds of things you see built in backend. But in the systems I usually see from my customer, these big monolithic systems, they try to solve both problems with the exact same solution. That is, I got some front-end system and some back-end system that are both talking to the exact same database. And with larger and larger systems, we very often find that that same system in the database that is used to build the back-end management is not remotely appropriate for the front-end systems as well. So good, that's equivalent in the real world of like, instead of me walking up and seeing a menu, I see like a spreadsheet with like a tab open. Like, okay, this is the prices for today. Like, you never see that, right? You don't actually see the back-end system from the real world perspective. You see this nice, pretty, stylized menu that is there to help you make your decisions. So it's very difficult to try to solve these two very different problems with the exact same model. They have two very, very different characteristics in the use cases. In the read scenario, of course, I could actually be pulling data from a lot of different sources to be able to show to the end user. And so I'd really want two different solutions for this heavy read model versus this heavy write model. So yeah, let's just like chainsaw the database in half, right? If only it were that easy. Because we still have to figure out how to get these databases to talk to each other. So we can use something like link servers, right? That's always a good idea. No, don't do that. SSIS packages. No, boo. Yeah, so we have to figure out how these different, how that backend system can communicate changes to the front end system. If I look at the real world as well, I want to see how these different pieces are going to interact with each other. What we find that very often is that updating the menu in the real world is more on a scheduled basis. So it's not real time, that is. So if a business person makes a decision on a price, it's not like as soon as that lever clicks in their brain that a new price shows up on the menu. Because one, that's not a very good experience to the end user. Like going to a restaurant and seeing the price change while you're at the restaurant is like, I would leave, right? I wouldn't shop. I wouldn't be there anymore. So it's more on a scheduled basis. Like typically it's like nightly or whatever, like when the shop is closed, then we'll go ahead and update the prices if we want to. But again, it's something that the business decides how often and exactly when those new prices go out the door. The other thing I see is the menu is immutable. That is, it can't have like the waiter being like, ooh, that's too high of a price. Scratch it out. This is a better price. No, it's like even though the data is now moved out to these menus and it's physically duplicated, right? It's not like the person reading the menu can be like, no, I don't like that price. I'm going to have something else. You know, I guess it would be nice, but you don't ever actually see that. So even though the data is duplicated, right, physically duplicated in the real world, no one screams and like cries murder, right? Even though I have prices printed on dozens of menus, it's not like there's some DBA in the background like, wait a minute, that's duplicate data. Oh my God, let's get that back into one system again. Like the real world is able to deal with this messiness of duplicate data, so how come our systems can't as well? So in this case, when I want prices to update, then we can use a similar kind of interaction we saw earlier, which is to publish out notifications saying, hey, price has changed from A to B, so I need everyone to go then update their menus. And if I have more than one store or more than one restaurant, then each of those gets that like daily email, whatever, of here are the new prices for today. So in this case, the publisher will keep track of who all the subscribers are, so it knows who to send out these different menu information to. It's going to have a durable format as well, right? I'm not just going to yell out to my different stores, price changed, or just like call them on the cell phone. I'd probably send it in some sort of durable format so that they don't lose those pricing updates. This will create an individual message per subscriber so that if something goes wrong in processing those menu updates, it doesn't affect any of the other stores. So if store C closed, or their mail is not delivered today for whatever reason, or they don't have their email, whatever, the other stores can still successfully receive and process that message. So we've got a durable messages to each of our subscribers. Each of our subscribers is unaware of each other, so there's no coupling between all the different stores. They can process that message independent of each other. And again, if one store is closed, then the other menus can still continue to be updated. So in this picture, when I have a pricing change that needs to go out, is business going to stop if that store doesn't process that message right away? And this is usually the argument I have to get into with when I'm talking about splitting up a read-heavy database from that transactional write system in the back end. It's like, well, then it's going to be out of date, right? It's stale data, and stale data is like the devil, right? But in the real world, we have stale data all the time. We, in the real world, are just able to handle that by saying, well, in the case where these things don't quite match up, then we may have to have some other kind of business process to handle that actual messiness. So in this real world, if store A, B, and C don't have exactly the same price at all times, does anyone care? Like, am I physically driving to each of these stores to check to see if the prices are exactly the same? Probably not. It would be weird though if I see like different price online versus physically in store. But it's not something that me as a customer really needs to know about or be aware of, that these different stores may not have exactly the same price on any given day. So if it doesn't affect the end user, and it's not severely affecting our bottom line, then we, in the real world, accept this kind of messiness and just kind of move on with our lives. So, some parting thoughts here. The constraints of the real world haven't changed. Just that the latency is much shorter. But latency is still not zero. Not everything is entirely instantaneous. Even though we may use like gRPC and all this stuff where latency is very short, it's still not zero. So we still have the possibility where things get blocked and delayed. The solutions for the real world can be applied directly to a distributed world because the same kind of principles we want to run independent systems and people in the real world are the same kinds of principles we want to apply to our virtual world as well. So us as humans like to have autonomy and agency. We like to be able to do our own thing without being told what to do all the time. And so our services are better designed with those kinds of characteristics in mind as well. So the real world solved these distribution problems with messaging and conversations and coordination. So if we just apply those same kinds of solutions that the real world has already figured out to our world, then our systems can be healthy and be successful as well. So thank you very much. That was effective microservice communication and conversation patterns. If you have questions, I'll be here afterwards. Otherwise, have a great rest of the conference. Thank you.